Welcome to the Practical Stats webinar for October. This is Dennis Helsel. I'm the one giving the webinar today. And the webinar is Never Worry About a Normal Distribution Again. And instead, I'm going to recommend that you use things called resampling methods. And the common names for those kinds of things often are bootstrapping for doing intervals and permutation tests for doing hypothesis tests. So you don't have to worry about a normal distribution ever again. That's not totally true, but it's a lot closer to being true than it has been in the past. So let's move on to the subject. The problem is that field data are usually what's called skewed, which means it's not a normal distribution. That skewness is caused by a zero lower bound, and by outliers that are almost always on the upper side and not on the lower side. So if we get data that look like they're pretty far out from the rest of the data, they're on the upper end only, and so that's skewness. A normal distribution does not look like that. Its data do not look like that, and so if you run parametric tests which assume a normal distribution, or compute confidence intervals that assume a normal distribution, and your data do not look that way, the result you can get back can be wrong. In particular, the intervals are often inaccurate, and I'll give you an example. And the tests often do not find differences that are there, and so they have low power to see things. Transformations aren't the answer. If you have data that are skewed, people often take logs or some other transformation. And when you do that, you're running tests and computing intervals on the logs, and when you transform them back, they don't have the mean inside the intervals. They're not dealing with differences in means for the tests. They're looking at geometric means at that point, which is one measure of a median. So it's not a mean, so you're no longer computing intervals on means if you take a transformation, whether it's a log or something else, and you're not testing for group differences in the mean. So a problem for many, many years in statistics has been, if you're interested in a mean, you have moderate sample sizes. I'll call moderate less than 50, either for computing an interval or per group if you're computing a test. Then this mismatch between the shape of the data and the shape that's assumed by the interval or the test will cause problems. And you'll get back results that may not be quite correct. So let's start with intervals. T-intervals assume the data follow a normal distribution. When you have a T statistic, that's an assumption. You can know that that's based on an assumption of a normal distribution somehow. So it assumes either that the data are normal, or that there's sufficient data, and the question is how large, how many observations is sufficient, that the sample mean follows. The distribution of it follows a normal distribution. That's something called the central limit theorem. I'll give you a picture later on. I won't really go into it in detail, but it is something that is a function of sample size, and you need a fair amount of data. The rumor has always been 30. It's not that. It's much larger than that for the central limit theorem to kick in. So if you just have a moderate amount of data, 50 observations, 20 observations, 10 observations, and you're trying to compute intervals and you use a T-interval, you don't have a lot of hope that that interval is going to be accurate. One of the big problems is that T-intervals won't include the true mean, which is their primary goal, as often as the confidence level suggests. So that if you compute a 95% confidence interval, it should include things. It should include the true mean 95% of the time, and it won't. So on the second problem is that lower ends of the confidence intervals are usually too low. The skewness with outliers on the upper end inflates the standard deviation, which means the intervals get wide, And that may match some of the data on the upper end where you have outliers, but it shoots it way low on the lower end. And so the low ends are usually, of the intervals, are too low. They're possibly below zero. If you do have an interval, a lower end of a confidence interval that goes below zero, and you're dealing with something that never goes below zero, and most of us, that's what we're dealing with, concentrations and other things, then that's a clear indication that you've used the wrong procedure. So here's just a picture of what might happen. You compute a 90% confidence interval. The meaning of that is 90% of the intervals computed under those conditions should include the true mean. The true mean here is the vertical black line called mu. And the blue ones here, the blue confidence intervals, include the true mean inside. That's good. The red ones do not. That's not good. And we should expect, if it's a 90% confidence interval, that 1 out of these 10 intervals does not include the true mean. But here we have 4. And that's just the result of skewness. So that's one of the effects of skewness. So the solution are resampling methods. Bootstrapping computes confidence intervals without assuming a normal distribution. Permutation tests do the same. And what they do is they use the observed distribution of the sample data, that the shape of the sample data is considered the best estimate of the data out in the field, not a theoretical distribution. So that all the information that you need about the underlying distribution out in the field is given to you by the sample data that you've collected. So here's just one simple example of a data set that I had lying around of mercury concentrations. I computed the T intervals. These data are from the box plot. You can see they're not a normal distribution. They're not the typical right skewness, but they're not a normal distribution. And the T interval is a lot wider than the blue bootstrapped interval. And so that's one of the benefits of using bootstrapping. Both of them were 95% intervals. So you get more precision with bootstrapping often if the data do not follow a normal distribution. How does bootstrapping work? It's something called resampling with replacement. I'll give you a picture. But let's suppose you had a data set of 7 observations. You would randomly choose, and look, you're going to see that you really want the computer to do this, randomly choose and then copy the value in the data set of one of those 7 concentration values that you have measured. And so it's randomly, each one has the same probability of being measured. So whatever 1/7 is, you'd randomly pick one of those and put it in the first row. In a second column, let's name it resample number 1. Then you do the same thing for row 2. And you'd randomly pick one of the 7. It could be the same one that you just picked, or it might not be. Each of the 7 have the same probability still. Copy that value and put it into the second row and do that till you fill up the first column of the same number of observations, 7 in this case. And you've got your first resample. So you would do this then, or the computer will, several thousand times. Typically somewhere between 2,000 and 10,000 is used. The higher values these days, because it doesn't take a modern computer much time to do that. So you have these resamples. All of the values in those resamples come from the original observations. So here's a picture of that. The blue data on the left are the original data that we've collected. There's 7 observations here. It has a mean of 18.1. That's going to be our estimate of the mean. Bootstrapping really doesn't care about the middle of the data. What it wants to try to do is tell you what the variability of that estimate of the middle is. So the mean is 18.1. The question is, what's a good, accurate 95% confidence interval on that mean? So here is the first bootstrap resample. First was picked was 16. That came from right there on the left side. Then 14, then 28, then the 16 was picked again, then 12, 24, and 14. All of these values came from the 7 original observations, but they're not entirely in the same proportion. 16 was sampled twice, and there must be that one of them then was not sampled at all. So here's the second one, a different set. And then the means are computed for each of these thousands of resamples. That gives us a picture of the variability of an estimate of the mean of 7 observations, based on 7 observations in your data set. And so here's a picture of what all of those thousands of means look like. This happened to be in a data set that had 40 observations instead of 7. But other than that, you can think of it the same way. So here's a picture of those, I think this case was 5,000 resamples. This does not look like a normal distribution. It has 40 observations. So 40 is not big enough for everything to look like a normal distribution. It depends on the skewness, and the data that we deal with are typically strongly skewed compared to what many other disciplines look at. So the fact that this looks skewed, looks more like a hydrograph, that if you split it sort of down the middle, wherever the mean is, the left and the right do not look the same. That's telling you it's not a normal distribution. And the central limit theorem would tell you that it was a normal distribution. So 40 is not enough. All right, so we have these 5,000 estimates. What do we do with them to bootstrap? Well, let's suppose we wanted a UCL 95. That's a value that 95% probability that the true mean is below that and only 5% that it exceeds it. So what do? We compute the 95th percentile of these bootstrap estimated means. That's a value of 37.41. 95% of our estimates are below that. Only 5% are above that. So that's the red line here. That's the one-sided confidence bound. If you wanted a two-sided confidence interval, 95%, you'd go to the 2.5 percentile at the low end and the 97.5 percentile at the upper end. So there's 2.5% beyond those two values, to the left and to the right, or a total of 5% of the estimates in total outside of that range. So that range from 3.73 to 43.39 in purple is our estimate of the 95% confidence interval on the mean. So that's a bootstrap UCL and a bootstrap confidence interval. That bootstrap estimate will reflect the shape of the data. The confidence interval may not be and probably won't be symmetric. A t-interval is forced to be symmetric mathematically. This fits the data better. I've already told you about the percentile bootstrap. That's what I just demonstrated by computing the percentiles of the bootstrap estimates. There is another method. It's just an adjustment of the percentile bootstrap. You compute the percentile bootstrap and adjust it for bias, called the BCA bootstrap, stand for bias corrected and adjusted, I believe, something like that anyway. And it's an adjustment for skewness. It requires some data. I would do that if you have something like 50 observations or more to begin with in your data set. It requires an estimate of the skewness to adjust the percentile bootstrap. So those are the two most commonly used ones. With small data sets, let's say 20 and below, you're likely not going to have really a good estimate of the range of the data out in the field and the proportion of data below any values out in the field. And so the bootstrapping won't help you there because you're not starting out with a reasonable estimate of what the values are likely to be out in the real world. So with 20 observations or less, that's my rule of thumb, and you'll find it in other books and journals as well. But with 20 observations, I would recommend not using bootstrapping to fit a distribution instead to the data. It's likely you won't be fitting a normal distribution, though, so you're still not going to be doing a t-interval just on the raw data that you have. Is it easy to compute the bootstrapped intervals? It is with software. Here is the command that we have in the Applied Environmental Statistics course. It's fairly simple. You put in the name of the column of data and the confidence level you want. The default for that is 95. You don't even need to put that in if you want a 95% UCL. And you get back the result. Takes just but a second. So that's pretty easy. R itself has a bit more complicated procedure, but it's still not terrible. I like this one better, of course. So it's easy to do these kinds of things in R. R is free. Here is another free program called PAST. And PAST, which you can find on the internet, it's actually very good. Statistics software package. It's not as comprehensive as R, but it's good for many things that we do. And if all you have to do is check the bootstrap button here. And instead of the usual t-intervals, it'll give you back bootstrapped intervals on the mean. And here's the lower and upper ends of a two-sided 95% confidence interval. So it's more common to find these in software. Is the bootstrap well accepted? Yes, it is. And the author of it, who in 1977 developed it, is named Bradley Efron at Stanford University, was given last year the International Prize in Statistics for developing the bootstrap. And so that's kind of equivalent to the Nobel Prize or something. It's the most prestigious prize in statistics. So yes, it is well accepted. Here, in the process of his being awarded that, some folks counted the number of journal articles where the bootstrap was used. This would have been early 2018, so early last year. And in chemistry, it's about 3,700. And let's go down to environmental science, 14,000. Up at the top, agriculture and biological sciences, over 44,000. I would guess that a number of those papers that they classified as biological sciences may have been environmentally oriented biology papers. So there's thousands that have already been used in the disciplines that we're associated with. So it's well used. This is just a statement that it was awarded to Bradley Efron. It's because bootstrapping has saved countless scientists and researchers the headache of finding a way to assess uncertainty in complex problems by providing a simple and practical way to do so in many seemingly hopeless situations. What does that mean? It means there's situations where we don't have a mathematical definition of what we want to compute. Here's one example, fairly simple one. And it's been applied to a lot more complicated things in genomics and other things. But here's a simple one, the Thiel-Sen line, which is the non-parametric straight line model that goes along with the Mann-Kendall test for trend. And computing a confidence interval on that. At least I've never seen a mathematical formula for that confidence interval. There's one for the slope, but not for the line itself, incorporating the intercept and the variation and how it changes. Like regression, the variation is wider at the ends than it is towards the center. So here's a bootstrap estimate of that. That was written by Kirk Cameron with MaxStat Consulting and made available in the Unified Guidance, CPA's 2009 document that was on groundwater statistics. So these kind of things are out there and available for you to use. When might a t-interval work well? When you have a normal distribution or a whole lot of data. The US EPA, that's, I believe, in a document related to ProUCL software, said that they thought that about 100 observations were needed for skewed data to really rely on the t-interval being a valid way to produce a representation of where the mean might be. And I think it's closer to 70, but that's okay. You get the picture. So it's a lot more than 30. And we just saw an illustration where 40 was not enough. So it is a function of skewness. We have generally really skewed data. We have data that are not going below 0. We don't measure things that go negative usually. So bootstrapping is valid regardless of the shape. It works well for a data set that would come from a normal distribution. It works great for sample sizes 70 and above. So there's really not a need to go for something else. Unless you don't have a lot of data. So for data sets below 20, this isn't the main topic of this webinar, but you get more of that in the class. You can use some tests to see which data fit distributions the best. Here's a data set which had a pretty good fit for log normal and a gamma distribution. So these probability plots look nice and straight. The normal does not. And so those software, this is from Minitab, I believe, but you can do it in R and others. Once you pick which one you want to use, you would not want to use the normal. And once you pick a good fitting distribution, you can have it compute a mean and a standard deviation, or UCL. It is not just a matter of taking logs and transforming them back. You have to do some mathematics to get something like a UCL back in the original units. But that's not for today, other than to say it's there. And you'd have to do that with smaller sets of data. So bootstrapping is widely available. It's distribution free. It provides accurate interval estimates when data are not normally distributed, as well as when they are normally distributed. It provides estimates. Let's see. You can compute estimates of variability that have no known theoretical equations. So I gave you that example with the Thiel-Sen line. It's used in a large number of scientific disciplines. So there's no need to use the t-type statistics for computing intervals or UCLs. So that's bootstrapping. Second topic is permutation tests. Very similar kind of thing. These are related to bootstrapping. They are resampling methods. And the problem, again, is that most data in environmental science are skewed. The mean is used as the measure of the group center, and then a test, usually t-tests or ANOVA, are run to see if the means differ. If they don't look like a normal distribution, in the past, people have either done non-parametric tests, that's great, and they're very effective. They just don't test for difference in means. They test for difference in medians or distributions. Or people take logarithms or some other transformation and then run t-tests in ANOVA, that's great, but they don't test for differences in means then. They test for differences with logs, geometric means, which are estimates of medians. If you use other transformations, it's still a difference. It's not a mean that's being tested, it's a median that's being tested. So doing a test for means, when means are really the target, with skewed data has been a problem until the 1970s, 1980s. And what is the problem? It presents in the sense of p-values in those tests being too high, low power to see differences, so you don't reject when you should, you don't find signals when you should, you don't find contamination. So you get faulty conclusions of one sort or another. Here's an example with two groups of data. The one that says down gradient on the left, downgrad, is not a normal distribution if you test it out. On the right was the up gradient data. They only collected 3 observations. So while this box plot does not look like a normal distribution, it's only based on 3 points. And you really can't test normality with 3 points. You're just not going to reject, even if it were non-normal. So you're kind of in this world where, well, this one's not normal, and that would right there invalidate really using a t-test for this, but you don't know about the other group either. So what do? Well, one way is just to hope and do a 2-sample t-test. And so that's what I've done first. It assumes that each group's data follow a normal distribution and that each group have the same variability, the same variance. And that's certainly not true here either. Typically, our data violate both of those assumptions on a very common basis. So here's a picture of the means. The mean of the up gradient group was 4. The mean of the down gradient group was 1/4, approximately. So a 16 times difference. All of the data in the up gradient group are higher than all of the data in the down gradient group. When you run a t-test, because of the violation of those assumptions, I presume, you get back p-value of 0.14 and would not say that the means are different between these. So that's the real world. What can you do about it? You could run a permutation tests. And here, what we're going to do is say, well, if the null hypothesis is true, then the mean of group 1 is equal to the mean of group 2. And what it's saying is that the other characteristics are also the same. Variances are similar as well. So if all of that is true, then the concentrations are really what is usually called exchangeable in statistics. In other words, if you had a value from group 1 and the null hypothesis is true, it might have just as well come from group 2. So the classification into groups really isn't significant if the null hypothesis is true. So it doesn't matter, in a sense, which observation came from which group if the null hypothesis is true. So that's what we're going to do. We're going to create a picture of the null hypothesis by shuffling or rearranging. Usually it's done with the group assignment. It can be done with the data values also. But we're going to change the relationship between an observation and the group that it came from. And we're going to do that rearrangement something like 2 to 10,000 times. Or if there's only a smaller number with smaller data sets, we'll do it all the possible times, all the different rearrangements that could occur. And for each rearrangement, we're going to compute the difference in the means for each shuffle, for each situation. And together, all of those means, in a histogram like we saw with bootstrapping, all of those means are a picture now of the null hypothesis. So here is the way to do it. This is the one that we use in the applied environmental statistics class. It's simpler than the real one back in R, but it works fine in R. So this is the permutation test for 2 groups. And the first column is the data, and the second column is the group. And for this particular set of data, this is the Molly data, which were the ones that had the box plot here, and the ones where the t-statistic was 0.14. Same data, just not assuming a normal distribution. The p-value is 0.0018. It's saying it's very unlikely that you would have split the data up into 2 groups randomly when they were identical to each other and put all of the data in the up gradient group that were higher than all of the data in the down gradient group. And it is pretty unlikely that that would happen. So it tells you what the probability of that happening is. It's about 18 out of 10,000 times. So it's a pretty small probability. And that's a very different result. That difference is the difference in the power in the 2 types of tests. When you assume normality and the data are not normal, you're leaking power. A permutation test won't lose that power. Here's the official way in R, at least one of the ways of doing it. It's with one-way _test command. Actually isn't any simpler or isn't any harder to type. And you see that it gets essentially the same result. These permutation tests, because they do different rearrangements, unless they're doing all possible ones, different rearrangements each time, they'll get slightly different sets of 2,000 or 10,000. And so the p-values will be slightly different. That's okay. Both of them tell you 0.0018, I think it was before, and 0.0013 is a whole lot better result, even though they're not identical, than an identical p-value of 0.14. That's 0.14 all the time, and it's consistently wrong. So, are these accepted? Well, one of the persons who developed the field of statistics, Carl Pearson, back in 1935, said, we're going to do what are now called, I don't think he called them this, parametric tests. He did know of t-tests by then. We're going to do these type of tests to produce results that are only approximations to the true result. And the true results would be found by permutation or randomization. I think he used the word randomization procedures. We can't do that. We don't have the computer power. He didn't say that, but he essentially said that same thing. We don't have the technology to do all the possible 10 billion combinations. So we're going to have to do some math to do approximations. And that's when they developed the parametric type procedures. And it's elegant math, but it's only an approximation. And the approximation only works when the data are like what's assumed by the approximation. So yes, they're well accepted in statistics. And how are they computed? I'd gone through this once before. Let me see, I can give you an example. Here's a simple, again, 7 observation data set, split into 2 sites, site 1 and site 2. Site 1 with a clear background, site 2 with a blue kind of background. What we're going to do with a permutation approach is to first compute the mean in each group for these, so the mean of site 1 and mean of site 2, and put those aside as the truth based on our data. Then we're going to rearrange those location identifiers. So the value of 6, which was in site 1, now becomes site 2 just randomly. 5 stays in site 1, 10 goes to site 2, and we've got 2 site 1s down below. So that's our first shuffle. Then we'll do that. We'll let the computer do it 10,000 times. Here's the results from a data set that we'll see a little bit later. So the results would have been developing a test statistic. The test statistic in this case is just the difference in the means. So the means of site 2 as they've been reclassified versus the means of the data in site 1 as they've been reclassified, and that reclassification gets changed 10,000 times, so the means get changed 10,000 times. So here's a picture of what those might look like, still skewed. Here was the observed test statistic, which would have been the difference in this case between the means. So that's our measure of the signal of the original data. The proportion of the results that are equal to that or above that is the p-value. That is the definition of a p-value in statistics. The probability of getting the result that you got with your data set or something more extreme. And so for this permutation procedure, the blue bars are all the picture of what the null hypothesis looks like. You might have gotten any of these results with a certain probability, and so the probability of getting a 2.36, which is what we did get, or something more extreme, is about 4%. When you assumed a normal distribution, and this would have looked, if everything had held to be the assumptions of a normal distribution, would have looked like more like a normal distribution of these blue bars, the ANOVA p-value was 0.07, the parametric test. So there's still a loss of power. This data set, which we'll see in a few minutes, had 50 observations in each of 4 groups. So it was not a small data set. And it still loses some power. So if the mean is the objective, use a permutation test. What this implication is that you don't need to test for normality first. That should not be the first step in a flow chart of what to do. That is very old school in terms of statistics. What would you do first? Decide if you're really interested in means or if you're interested in something else. And if you are interested in means, use a permutation or bootstrapping procedure. Permutation tests don't care about the central limit theorem. They don't need it. They use only the observed data and all the possible rearrangements of the data. They have more power than the traditional tests. They can be used with censored data. I won't go into that today with non-detects. And they're less affected by outliers and unequal variance than our parametric tests. The number of results, you don't really care about this, but I always think it's interesting. The number of permutation results increases quickly. So we had a small data set with that Molly situation back there, and there was only 560 possible ways to rearrangement, so the software computed all 560 results to give you back a p-value. But if you had 2 groups as small as 20 observations each, split evenly, so 40 observations total, split into 2 groups, there's 137 billion different arrangements, and so the computer's not going to sit there and churn all those out. So what these tests do, if there's too many to do all possible, is again, compute somewhere between 2 and 10,000, or you could do more these days. 10,000 only takes a second or 2. All right, so this was that data set that we saw, the blue bars a few minutes ago, 50 observations in each group. The analysis of variance has the p-value of 0.07 because it's assuming normality, and these data are certainly not a normal distribution. These outliers destroy any hope of that being a normal distribution. Got a zero lower boundary that things are smashed against. So those are just classic characteristics that are not normal. And so this is the process again. Compute a statistic. Since this is a multi-group test, not instead of just taking the difference in means, what's computed here is the F ratio. It's a statistic using all 4 groups. And just doing that 10,000 times after the data have been reshuffled between the groups. The ANOVA test gives back the 0.07 result. If you looked at the residuals, here's the normal probability plot for the residuals with a big curve. So that's telling you the data are not a normal distribution. You're in trouble if you're depending on the ANOVA to give you an accurate p-value. You could take logs. Here's a nice probability plot. The logs would be a great set of units, except you're no longer testing means. So you could do that, take logs, just you have to decide, well, I'm really interested in looking whether the medians are similar or not means. If you were, you could do that. Here's the ANOVA on the logs, which gives me a p-value of 0.007. The medians appear different. Or you could run a permutation test if you're interested in means. And the p-value is 0.047. So again, this was a fairly large data set for the types of data that we usually have. And it's still a benefit to use the permutation procedure. And the permutation procedure, again, would have worked fine if all of the 4 groups of data had a nice normal distribution, or if we had 10,000 observations in each group, and so the central limit theorem would have held, then it would give you the same result as ANOVA. Here's just another way of looking at those blue bars. This is R's output, I believe. The p-value is 0.047 for the permutation procedure. All right, so we can use permutation tests in other situations. I'll just give you 2 additional ones quickly. One are matched pairs. So you've got data. In this case, you had lead measured in soils, and it was before and after a fire. And so the question was, has there been a difference? And they may have expected, I think they did expect an increase after the fire. But for this, it doesn't matter. So we are seeing if the lead concentrations, and let's say the mean lead concentrations in 1996 before the fire look the same at the same locations. They're matched pairs because they're going back to exactly the same lat-long locations in 2001. And the question is there a difference? And you can take the differences of 2001 minus 1996 and do a box plot of those differences. Looks like this, and it looks fairly symmetric, but you've got this observation number 30 down here and observation 50 up here that are farther out. They happen to be on both sides, but farther out than what you would get with a normal distribution. This turns out to test to be not a normal distribution. The question is that a problem? If you have symmetric outliers, generally, that's not as big of a problem for a t-test or similar tests than is outliers and skewness just in one direction. But it's not a normal distribution, so do we have a problem? We run the t-test, that's the one in the box here, get a p-value of 0.085, and we scratch our heads and say, well, there wasn't a normal distribution, so is this valid or not? That's when a permutation test is a good thing to do, or it would have been a good thing to do it and just ignore the t-test. So you can do a paired or matched permutation test. Its p-value is also 0.08. So the p-value of 0.08 for both tests tells you that the t-test really wasn't hurt by the non-normality. So what the permutation test does is give you a confident p-value that you can report. There's no worries. And the second example is there's a wide use of permutation tests now in multivariate procedures, because it was terrible for years to try to evaluate multivariate normality for things like multivariate analysis of variance, MANOVA. Multivariate normality is even more restrictive than, let's say you have, in this case, 7 variables. Even if all 7 variables had a normal distribution, they may not be multivariate normal. So it was a very restrictive assumption, which made people uncomfortable in running these parametric procedures like MANOVA. So these days, many software packages are using permutation tests for multivariate procedures, multivariate tests. So here's one example, one I use in classes that I teach. Atrazine concentrations, they were classified as being above or below 1 microgram per liter. So I'm going to use that for the 2 groups here, is the concentration values. And then the site characteristics, there were 7 of them, including flow percentile, how much of a flood was it on the stream. These are surface water concentrations. Percent corn grown in the basin, other characteristics. Those 7 variables are what we're going to use here as the things that we're testing. So we're really saying, when we divide this up into atrazine being above 1 or below 1, do I have different site characteristics as measured by these 7 characteristics? Here's a multivariate graph called NMDS. I won't go into that in detail. Actually, I won't go into it at all, except to show you that the data that are less than 1s are plotted in the red dots, and they're pretty much lying off to the right of the mass of the data that are above 1, that are in the blue dots. So we do have this separation left to right on this plot. And so that's going to be an indication that these 7 variables, at least some of them, are differing between the less than 1 group and the greater than 1 group. So I'd like to test that. That test is commonly called these days PermaNova, permutation ANOVA. Developed, I think, certainly first used that I saw in the package called Primer. In Primer, all of its multivariate procedures are done with permutation tests. And it's done in R with the Adonis function. And so you can run a permutation analysis of variance, a PermaNova. You can also run a traditional parametric MANOVA and compare them if you want. The PermaNova doesn't have the assumptions of a normal distribution. This would be within this whole multivariate dimension of 7 site characteristics and 1 chemical measurement. Somehow those are big, huge bell-shaped curves in multidimensional space, assumed by the traditional MANOVA. Oh, and it also assumes that they have the 2 groups, the less than 1 and greater than 1s, have kind of an equal distance in all 7 or 8 dimensions, so that their variances, the bells, are the same size in multidimensional space. So you can see, at least from my verbal description, that that's a pretty restrictive assumption. You can quickly use in an R this Adonis function, get back a p-value of 2 times 10 to the minus 4th. Procedure rearranged the classification into groups less than 1 versus greater than 1. Did that 4,999 times. Here's the 4,999 test statistics. Most of them are down at the low end, going up to around 15. The observed statistic that we got in our data set is 281. So it doesn't even fit on this curve. So this observed statistic is higher than all 4,999 of the re-sampled, permuted sets of data. This is the null hypothesis, and with the null hypothesis, it's very unlikely to get the one result that we got with our data. So that's a p-value, because it's the highest out of 5,000, it's 0.0002, 2 out of 10,000. Okay, and there was no assumption of multivariate normality done. So the summary for permutation tests are that there's a whole lot of ways you could do permutation tests. There's tests for differences in variability. That's alternative to the traditional F test of Bartlett. We saw the matched pairs. That's alternative to the paired t-tests, means of two or more groups. So alternatives to t-tests and ANOVA. You can do testing differences in regression slopes with permutation procedures, and so on. So there's a lot of possibilities. The software is there waiting for you to use it. So they can be used instead of parametric tests, avoiding the assumptions of a normal distribution and equal variance, which our data, usually violate. There's no pretest for normality required. There is more power to see differences between means for skewed data than with parametric tests. And so we can finally see differences for groups that we're interested in the means as their center when we have skewed data that are common. So that's been a huge relief. Where would you find these things? I've already mentioned R and PAST. SAS and STATA are two commercial packages that have included them. I'm sure by now there are others. I forget how long ago. It's probably at least 2 or 3 years since I checked these out. At that time, Minitab was starting to include them, so there should be others. So I would use that as the availability of bootstrapping and permutation tests as one of my criteria for what software should I use. Training, our applied environmental statistics class is online now and has been for a couple of years. We go into those in detail. If I'm not certain I'm going to, if I put up a third class, I've put up so far the 2 most popular classes that I've taught over the last number of years, many years. The applied environmental statistics class and the non-detection data analysis class. The third most popular was my multivariate class, so I might put that up. If I do, it'll be out early next year. We'll see. Some books. The new version of statistical methods in water resources, which at least the last time I heard has not been out yet, published by the U.S. Geological Survey. They said it was going to be in 2019. They have 10 weeks left to meet that deadline. We'll see. Introduction, when it is out, I will shout it from my webpage. So you can always check there. Or you can sign up for our newsletter and it'll be shouted out that way too. Introduction to the practice of statistics, bootstrap methods and their application. That third one down is kind of a classic book on bootstrapping, has a huge amount of detail. And so on the bottom one is an early one where these things were applied to biological data by Manley. So there's references around. It won't be too hard for you to find them. Look for books written in the last 10 years or so, at least the ones applied to environmental science. There's a bunch of newsletters that are free up on our webpage. You can go and grab them in our news archive. There's a button there you can click for different topics. So if you click the perm test button, you get all the ones we've done, which are not that many, really, on bootstrapping and permutations. I think that's the list of all of them. So if you haven't already, type in questions into the question area. The ones I don't get to in a minute, I will compile them. So all of the answers to all of the questions and post them here. So let me look at the questions. So first one, David, for permutation tests, do other test assumptions apply? Homogeneity variance. I think I mentioned that earlier. No, not technically. Equivalence applies. That's not the same, and it's not as restrictive as homogeneity of variance. But in some sense, it's still like homogeneity of variance because you're assuming that both groups are the same. Both groups are similar. It doesn't matter which, that's an assumption of the null hypothesis in statistics. It's not an assumption of this particular test or that particular test. So you can't get away from that. So it does mean that if you have outliers in one group, let's say, and not in the other, when you do all these scrambles, when you resort all the data and run the test 1,000 different times, that those outliers are going to get smeared over into the other group. And the other group didn't have them to begin with if you only have outliers in one group. And that's a problem in a sense for the mean. Again, it is not a problem with the test. It's a problem with you're doing a test, so you're assuming that they're the same, number one. And two, you're working with a mean that's sensitive to outliers. How could you get away from that? The easiest way, because you're always going to, if you're doing a test, you're always assuming that the groups are the same to start with. So you can't get around that one, but you could use a test on medians rather than means. And then those outliers are not going to have the same influence. So you could just do a standard non-parametric test, or you can do permutation tests on medians as well as means. So technically, no, it doesn't have homogeneity of variance, but because you're doing a test, statistical test, it in essence is at least that they're the two groups, the technical term is equivalence, that they look the same. Second question, when would you transform data, we assume, with permutation tests or bootstrapping just for scale? Well, you may, but again, once you transform, you're not going to be dealing with means unless you know how to do the math, unless you know how to fit things back into the equation for a log normal distribution or a gamma distribution. So you can't just transform the data and do statistics in the transformed units and then say they apply to the original units. They don't, not in the way that you think. So again, a simple example, if you take logs, do a t-test, you are testing differences in the mean of the logarithms, which is not the same as the difference in means back in the original units. So if you're willing to give up interpreting means, then you can transform. With a permutation test, there's no reason to transform. So I would not transform. If I'm interested in means, I would not transform. And transforming yourself is different than fitting them with those other distributions that I showed one slide with the 4 probability plots. I think I said it came out of Minitab. They're doing the math of giving you back means once you take logs, or the means once you assume a gamma. They're not just taking logarithms. Okay, what are the advantages, disadvantages of bootstrapping versus a non-symmetrical distribution such as a gamma distribution? Well, once you get a moderate amount of data, I would put it up certainly above 20. Maybe I could be more cautious and say around 30 or 40. Then I don't think there are any disadvantages of bootstrapping. And I would use those. The disadvantages of assuming a distribution is if your data actually don't fit that distribution exactly, because they are parametric procedures. They're just a parametric procedure for a gamma distribution instead of a parametric procedure for a normal distribution. Gamma and log normal distributions are fairly flexible and fit different varieties of skewness. So they're more likely to fit your data better than a normal, but they're still parametric methods. So the primary time I would use one of these assumptions of a distribution is when you don't have a lot of data, like less than 20. And that's when what you're doing is you're projecting really outside the boundaries of your data set. And you're doing that with a model. And that model is that it's a gamma distribution or that it's a log normal distribution. But you're allowing there to be a possibility that you might get data the next time you go out and sample that are higher than all the data you've currently got with your 5 or 6 observations. So, or even 12 observations or whatever. So that's what you're doing when you're modeling, and that's you are modeling when you assume a gamma or log normal or a normal distribution. So once I get up into the realm of 30, 40, maybe observations, certainly I would use bootstrapping instead and permutation tests instead. Let's see, and I'm just skipping. If I don't get to yours, I will get to it when I do the file that gets stored up on the website. So if it is recommended to use over 70 to 100 values for bootstrapping, I did not recommend that. I think that's way too large. So don't misunderstand me. I was recommending to use 70 to 100. That recommendation and the EPA's recommendation was if you were going to run a t-test or compute a t-interval. So I'm glad you asked that question. I was not clear enough on that, I guess. The t-intervals and the t-tests are things that this If you're assuming data have a normal distribution, they do not have a normal distribution for this thing called the central limit theorem to kick in with the amount of skewness that we have is going to take 70 to 100 observations. So if you're going to use a model that's totally unrealistic for the type of data that you're collecting, the hope that you have, called the central limit theorem, that it doesn't matter, that's what is assumed. So we're not assuming 70 to 100 for bootstrapping. Okay. So you can use bootstrapping for your question goes on to say bootstrapping for a seasonal Kendall DLSN line. You can still do bootstrapping with smaller amount of data for that. So that requirement would be more applicable to computing t-intervals around a regression line if the data are not a normal distribution. Hopefully that's shocking for some of you. Okay, that was the point of this. Can you use permutation test scripts with censored data? If not, are there scripts available that are? Yes, there are permutation tests for censored data. There are scripts that have been written. You can find some in R packages. You can find them in our non-detection and data analysis course. So those are the two primary places. The R packages that have them would be the NADA package, NADA, which is based on the first edition of the book that I wrote, and then the ENV stats package. There's other places, but those are the two most common in R. The scripts that I write generally are simpler to use than the things that are available in R. That's the main difference. Okay, but there's no reason why the procedures cannot be, anything you can do, you can bootstrap it. Anything you test, you can run, you can use a permutation version of it. So if you use large sample sizes, greater than 600, can you perform ANOVA based on the CLT? I would assume so, yes. When using a permutation test, the calculations compare the median of two groups instead of the mean, right? No, that's the whole point. Glad you asked that question. Permutation tests can be run on anything. The primary usefulness they have been applied to has been for things having to do with a mean, because the mean is the thing that gets jerked around so much with outliers and skewness. The mean is the thing that's been a problem with computing a decent confidence interval or doing a decent job of running a test on. So non-parametric tests for years have done a great job of testing for differences between medians. So permutation tests are not, they may be, you may compute one on a median, but you're more likely to find them. The typical situation is on means because that's what's needed. That's the symptom that has needed a remedy, is saying something about means with skewed data. So that's the primary application for permutation tests, and certainly the primary one in environmental science. What are the advantages of using permutation tests? And I'm only going to do about 2 more just to save time. I don't want to go more than about 10 minutes more than what I tell you. So what are the advantages of using permutation tests against non-parametric tests? Well, again, there's really no advantage of using a permutation test on a median versus a non-parametric test. And in fact, they're very mathematically strongly related. Non-parametric tests are really just subsets of permutation tests. So they give you pretty much the same results. Permutation tests on means are much better to use than non-parametric tests if you're interested in a mean, because non-parametric tests, again, don't test on means. So kind of go back to something I mentioned earlier. Any flowcharts that you see that start off with, first thing you do is test for normality, throw that flowchart away. It has not been valid for 30 years at least. So what's the first step in deciding what to do? Make a clear statement of what it is you're trying to do. And are you interested in the difference between means? You're probably doing that if you're interested in mass or volume. Or are you interested in medians? That's medians or percentiles are a measure of frequency, so how often something happens. That would be the tests that I would use if you're doing things like, does one group have higher values than the other? That's a frequency question. It's not having anything to do with means. Is there a trend? Unless you're specifically interested in a mean, which is very unlikely, a trend is a frequency question. Are high values more frequent in later years than they were in the early years? I'd use a non-parametric test for that. So the very first thing is, what am I trying to do? Answer it in, I'm interested in means or I'm interested in percentiles, and then choose the appropriate test. In general, if you're interested in means, use permutation tests on means, which are the primary ones that you'll find in software. If you're interested in frequency questions, is one group out of the 4 groups, is one group higher, sitting up higher and it's on the plot than the others? Do I have contamination in that group and I don't in the other groups? Those are frequency questions. Use non-parametric tests. They really have, those kind of questions really have nothing to do with a mean, even though that's how many people have done it, because that's what you learned in your 1 semester class in a university, is tests on means, the classical parametric ones. All right, with that, I will end. Thanks for attending today. Goodbye.